we have now derived a phase diffusion equation. Well, the phase is essentially gives us the wave number via its gradient. So it tells us about compressions and expansions of the pattern. And that phase diffusion equation, as the name says, is diffusive. And importantly, that diffusion coefficient is not a constant, but rather it does depend on the wave number of the pattern. And so it becomes a nonlinear equation that way. And moreover, we see that d can be negative. Actually, dq is negative for q squared bigger, what I'm writing here, q squared bigger than mu over 3. And so that means if we look back at our diagram for the Ginzburg-Lambda equation, so the Ginzburg-Lambda equation, we have a control parameter mu, and actually the wave number we're plotting here is the deviation of the true wave number from the critical wave number when you think of the Ginzburg-Lambda equation as derived from another system yet. So that's why Q can actually be negative. But that's not really important here. So the important part here is that we have a neutral curve, which for the Ginzburg-Lambda equation is simply mu equals Q squared. And we have that outside that neutral curve, the state a equals 0 is stable, and inside that neutral curve, a equals 0 is unstable, and that's where we get the patterns. And now we get an additional curve, which is given by q squared equals mu over 3, which is always inside. Should be also a parabola, it's not very nice drawn. And here we have that the pattern is stable inside. When q squared is smaller than this number, then the diffusion coefficient is positive, where it's unstable outside. And this is, okay, this we derive for the Ginzburg-Lambda equation. And since the Ginzburg-Lambda equation describes weakly nonlinear patterns for all steady bifurcations that lead to finite wave numbers, this is really a universal picture near the bifurcation point. And now this instability at d equals 0 was first identified by Victor Eckhaus, and he did it using some sideband instability analysis, which we can do later. We'll see where we do that. But so this is, the Eckhaus instability is a universal instability for steady patterns. We did it for the Ginzburg-Lambda equation, and so we know it's universal near onset of the pattern. But let me emphasize another aspect. In all of our analysis, we did not assume that the patterns are small. The amplitude A was order 1. And so if you think of the Ginzburg-Lambda equation as a microscopic equation, I mean the basic equation, then you see you could do this thing at arbitrary amplitude. You can do the same calculation for the Swift-Hornberg model without assuming that the amplitudes are small. And then you get, again, this phase diffusion equation. It will again have a diffusion coefficient that becomes negative close to the neutral curve. And so you really have this as a universal instability of one-dimensional patterns. Because you can't do it for arbitrarily large amplitude, let me just show you one set of data where there was the stability was measured in tailor vortex flow, right? Remember, we have the two cylinders and rotating like that. And depending on the rotation rate, you get different strength vortices, but you can also change the vortex size by sort of just compressing the system, so to speak. And what's shown here are the experimental data, which are these symbols. These show, as a function of the control parameter, which is the rotation rate in this case, and the wave number, you see the stability limit. So inside here, the pattern was actually stable experimentally, and it was unstable here. And so what are these lines? These lines are the following. First, this is just a neutral curve for these vortices, calculated directly from Navier-Stokes equations. And then if you calculate from the Navier-Stokes equations, the Ginzburg-Landau equation, you get a weakly nonlinear description that is valid near the onset. And in this Ginzburg-Landau equation, you get this stability limit, the dashed line. And you see the dashed line agrees very well with experimental data near the onset of the pattern, as it should, because it's the Ginzburg-Landau equation is a weakly nonlinear description that's valid near onset. But if you don't go to the Ginzburg-Landau equation, but take Navier-Stokes directly and do exactly the same approach we've done here, except it's it's considerably more involved. But what you do is you just assume that the patterns are almost periodic, meaning the wave number varies only slowly in space and time. And you do exactly the kind of expansions, the same solvability conditions. You get a diffusion coefficient, and that goes to 0 at the solid line. And you see that indeed this long wave, well, we don't know about long wave at this point yet. I'll get to that in a second. But this instability really captures the experimental data very well. Okay, so as I just said, actually as a slip, that this instability here, this echoes instability, is actually a long wave instability. So what do I mean with that? So let's analyze this equation now. A very simple analysis. We know, of course, if D is negative, then we have backward diffusion and small perturbations grow. But we want to be more concrete or more precise. So let's assume we have a pattern with a fixed wave number and make a small perturbation around it. So, or in other words, we take let me see, where do we go? We make a perturbation calculation where we assume a phi is given by some amplitude times e to the sigma t plus I capital P capital X. So that means we have the phase is, you could imagine here an IQX in addition. Let me rather assume, yeah, I should do it this way. I didn't write that down right. I want to have this plus, and then we have Q times X. So what I mean is that the phase, if the phase is simply Q times X, that corresponds to a pattern with a fixed wave number Q. And we're assuming such a pattern, and then we expand around it, we make a small perturbation, and that perturbation allows a small modulation of the wave number, modulation of the phase, and maybe it's growing. And this Q is the Q showing up here. And so we expand then around that solution, and then we get the equation d phi by dt is equal to d of, maybe let's call this dq naught, just so we mark that this is a specific wave number we're talking about. And we get this diffusion equation. And of course, if we then plug in our perturbation here, then what we get is that sigma is given by d of q naught minus p squared. So that means if d is positive, okay, then the perturbation relaxes. But if d is negative, the perturbation grows. And now you notice an important aspect. That growth rate increases quadratically with the perturbation wave number. So that means that when you take the equation as it is right now, that the larger the perturbation wave number, the faster the growth. And since in a continuum, you can have arbitrarily large wave numbers, you really have an ill-posed problem, because for arbitrarily large wave numbers, the growth rate is arbitrarily large. And so you really, to capture that regime, you need to have a regularizing term. And so if you, you can derive that actually, if you assume that d is small, so if you assume d is small, positive or negative, then with exactly the same approach we've taken, you go to one order higher, and then you get an additional term which I'm just going to add here. We're not going to do that calculation. And it's on symmetry grounds, it's a fourth derivative because of the reflection symmetry. And so, fourth derivative, if you then plug in that perturbation, you get an extension of this, and you get minus d4 of q naught times p to the fourth. And now you see that even if d is negative, assuming d4 is positive, which actually it is, at least in the usual systems, this is positive. And that means even if d is negative, for arbitrary large p, the growth rate becomes negative. So it's really, but the picture really looks like this. So you have, if you plot sigma versus p, so if d is positive, then you simply have the growth rate is negative, and it becomes more and more negative with increasing p. Then if d becomes negative, then you see for small p you actually have concavity upward, so you have parabola concave upward, and so it starts like this. So I should write like this is d negative, and when d is positive, oh, I did it exactly the wrong way around. Excuse me. So if d is positive, then the growth rate is negative. If d is negative, then for small p you have growth, but then the fourth order term kicks in and the parabola comes down here. And so if you calculate the maximum here, where the maximal growth rate is, sigma max, that's at some p max, and that p max is simply given by p max squared is equal to minus d of q0 divided by 2 d4 of q0. And so you see that when d becomes negative, meaning when it goes through 0, the maximal value of p is actually, well, initially at 0, and then it grows away from here. So let me draw just one more curve. If d is more negative yet, and I'm going to draw that in gold, then you have a faster growth here, and the maximum is shifted to yet higher values of p. And so that's what I meant with the long wave instability. At onset, the perturbation wavelength that grows is actually infinitely large. And then as you go further and further beyond the stability limit, meaning you go further out here, then the mode with fastest growth has a larger and larger wave number. And if you think about it, if you now think of a finite system, in a finite system, for d equals 0, you can't have that perturbation with very large modulation wavelength. So in a finite system, the stability limit is pushed to somewhat larger values out there where d is actually already negative. Now that's sort of a detail, so let me not ponder more of that. But important to note is that the Eckhaus instability is a long wave instability where the growth rate behaves like this. It's concave down and then concave up and then goes down also. And just to say that once more as a final statement, so this Eckhaus instability is universal for steady patterns, not only at onset, but even at large amplitudes.